Here we are in part 3. Let's talk about 3D math, and I'm calling this math problems you must be able to solve. And so we're going to start off with some review of some math problems you've seen before, and I won't go through the solution because you already know how to solve it. And then we'll get into a little bit more advanced stuff and we'll work through them. I often do get questions of, yeah, about that stuff I'm supposed to know how to solve. Can you give me the answers? And I'm not going to go through them here in the lecture because I don't think everybody wants to review that. You should have it back from 380 notes, and if not, of course it's in the textbook, and if not, see me later and we'll go through those solutions too. My hope is that by this point you're confident with taking on these basic ones, and by going into the more advanced ones, you'll gain that confidence. When you go back, after having done the more advanced ones, when you go back and look at the earlier ones, you're ready to go. You can do it. Okay, here we go. Starting with a little bit of a review. We definitely did this one in 380. This is classic reflection. You have some plane given a normal, unit normal, right? And some velocity coming in that you want to reflect going out. So maybe this is the ping pong ball bouncing off a paddle, or maybe it's a bullet ricochet, or it could be a laser beam, right? Maybe it's not really a velocity, it's a beam of light. Or maybe it's a reflection of like light for the specular lighting calculations. These come up, this reflection problem comes up very commonly. And I'll say, when I was interviewing at Universal Studios for a job there, this was my technical interview question. And I went in overconfident and cocky. I went into this interview and I just like, oh yeah, I know that. And I just wrote down the answer without doing the work. And I made a mistake. I forgot the 2 in it. There's a 2 in this answer that I forgot to write down. The interviewer was nice to me though, and you know, recognized my cockiness and that I just needed to be taken down a peg, and he reminded me, you know, please do the math and show me where you got that because I think you've made a mistake. And I did the math and then I realized, right, I forgot the 2. Okay, so that's my story. You've seen this in 380. Hopefully, maybe you don't remember, but hopefully you have the confidence to know it's always a dot product. So look for dot products, look for ways to add vectors together and get that answer. Okay, let's move on to another one that is similar, and that is closest point to a line. You have a line given some definition and some other point, and the question is, where is the closest point on that line to this target point? And that comes up in lots of different game scenarios. We'll see it a ton, and we'll be using it down the line. The thing to remember here is that occurs when the line connecting here is perpendicular. Let me draw it in. You connect a line from there to there, and that is perpendicular. This is the point we're looking for. And how would you get that? And once again, let me just say dot products, right? Do dot products, find some vectors, make some vectors, do some dot products. That'll get you some lengths, you know, do some vector addition, and you can come up with that point there. How about if it's not a line, but is it indeed a line segment? If it's a line segment and not a full line, what would you do? Well, we know how to get the line. We just did that. That would be, you make this perpendicular and you find this point. But it's not a line, it's a line segment. So the correct answer here in this diagram would be the end of the line segment. So what would you do? You do the same thing. You'd first do the line, get this point, and then you'd have to ask, is that point within the ends of the line segment? Is it in front of P0 or is it behind P1? If it is behind P1, as it is in this case, or beyond P1, the answer is P1. If it is down here in this region, it is P0. And if it's somewhere in between, then it's the point you already solved. The one thing I will say about this is that as you do the math, you'll find you're doing a dot product, and you should have something that is essentially, that is this distance here. At some point you will be getting that distance, and I would suggest to you that perhaps you got that length, not in terms of a length, but at some point you could have gotten it in terms of the parametric equation of that line. You're going to write this line as a parametric equation and call the parameter t. So if you make it t is 0 here and t is 1 there, then you can answer this question of whether t is between 0 and 1 or not. If t is between 0 and 1, then it's the point you got. If the t is greater than 1, then the answer is P1. If the t is less than 0, the answer is P0. Let's take it now into the next tier where I will actually go through with you the solutions. Here's another problem. This represents a plane now. So we're doing 3D. This is a plane with some normal. What you're going to need to uniquely define a plane, you will need a point and a normal that defines a plane. And you'll almost always have that. You may have the plane equation, although I'd say that's kind of unusual. More likely, you'll have the normal and some point on the plane. And what we're going to do is we're going to say, here's a ray. It starts at point R0 and it moves in direction V. And we want to know, where does that intersect right there? Let's draw that. Where, if we continue this, where is that ray going to cross the plane? What is that? Like maybe it's a laser and we want to put a little laser dot on the wall, or maybe it's a bullet and we need to make a little bullet hole on the wall at that location. Take a look at that, think about how you'd approach it, and then let's go to the next slide and we'll go through all the answer. There's a bit of a hint. We'll come back to it, but first you need to determine whether the ray is parallel to the plane. If the ray and the plane are parallel, then it won't ever cross. So we'll check that first. Let's skip that though. We'll come back to it. We'll see in a minute. Next up, we will want to make the plane equation. Here's how I make the plane equation. I'm given P0, I'm given N. I didn't put a little hat on there. I should put a hat on there. And P represents all points in the plane. So P is the variable. It's any point. It's every point on the plane. Every point in the plane must satisfy this condition that, that if I make a vector from that P to the given point in the plane, P0 is definitely in the plane. So if I make a vector from the given point to my point, make some vector, that line segment, that vector is definitely part of the plane. So if it is definitely part of the plane, that vector, then if I dot that vector with the normal, then that answer must be 0. The normal is perpendicular to the plane everywhere, and so P minus P0 dotted with N must be 0. I will use that as the basis to create my plane equation right there. Okay, and sometimes we'll make the D this negative value. Sometimes you'll see it as the positive value. It doesn't really matter. Whichever way you choose, just stick with that. All right, we will then write the ray as a parametric equation. So the ray started at point R0 and it moves along V, like let's say V is the speed per second maybe, or it's the speed per frame, or it's, you know, whatever scale that's in. And then T will be in that scale. Okay. So next up, what do? We have the parametric ray equation and we have the plane equation. We are looking for the moment when the ray intersects the plane. Let me do a little sketch here to remind us. We had a plane, that's our plane, and it has some normal, and then we had like a V, we have a ray. It goes R0, and it goes in direction V. So we're looking for the moment when these two things cross, or the moment that they're both true. This is a point that is in the plane, and it's also a point on the ray. So that means it's a point that is an R, that is also a P. Or simply, we're saying R of T equals P. These are equal at that particular spot. And so that's what we've done here, is we have simply taken what is R and stuck it in for the P. Right? We'll put that right there. Okay, let's take that to the next slide. Just rewriting that here to get us started again. And let's just do algebra now. Let's take a look first. R0 is a constant, V is a constant, T is an unknown, N is a constant, D is a constant. So this is an equation with only one unknown in it, and so algebra should be able to solve that for us. The first thing I'm going to do is distribute the dot product. So I distribute the dot product right on there, and I'll distribute the dot product v dot n times t. T is a scalar, so I can just pull that out of the dot product right there. So I've got that dot product, this dot product, t, and then here this constant d I'll bring down. All right, what's next? We're trying to solve for t. T is our only unknown. So let's isolate t. I'm going to take t and put this term over on the right-hand side. I've done that there. And now, how do we get the t all by itself? Let's divide both sides by v dot n. Okay, we'll do that. And of course, the minus sign, we're going to want to flip that over to the other side. So there you go. T has the value given by this. Now, I always say, this has got a division right here. There's a division symbol, and every single time as a programmer, every time I hit that divided by key, I get a little cold feeling in the pit of my stomach that says, oh wait, if I hit the divided by key, what if it's divided by 0? If I'm going to divide by 0, I'm going to get an exception, the whole thing's going to crash, it's going to fail. So that's bad. So before I even type that, I'm going to need to type if v dot n is either equal to 0 or very, very close to 0, I don't want to do this division. So before I even do the division, I'm going to need to check, is v dot n equal to 0? And if it is, we'll set this aside and we're not going to do it. If v dot n is not 0, then I've got my equation and I'm good to go. Okay. Assuming v dot n was not 0, then I have t. Now that I have t, I'd simply plug that back into my parametric ray equation, and I have the point back. I can get the point. Great. Let's circle back. So we've got the point, we got the t, we got the point, we know the point of intersection. We're done, except for that if statement I said we needed. If v dot n was equal to 0, we're going to have a problem. But guess what? If we go back, if v dot n is very, very close to 0, we know that v and n are perpendicular, meaning the ray is parallel to the plane. So the very first thing you do is that dot product. You do the v dot n dot product first. If that is close to 0, you don't bother with the rest of the math. Here's the rest of the math. So you do v dot n first. And this equation shows you that. I like this. I like to look at the math and understand that what this divide by 0 is telling you. That when you see a divide by 0 potential in your equation, it's telling you something. It's telling you there is no solution if that happens. Why would there be no solution? That's because v dot n equals 0 means the ray and the plane are parallel. So that's a good way of reminding yourself of that. So when you actually program this, do the v.n first. If it is non-zero, then calculate the rest of it. Don't bother calculating this part if the denominator is going to be 0. Okay, so that's the ray plane intersection. I went a little fast through that. So when you're actually trying to work this, maybe go back and do it step by step and pause and slow it down as you need. Let's take it to the next level. What if we're going to do the ray plane intersection again, only this time it's not a plane, it's a triangle. So for example, we're going to do our laser dot, and it's not just on an infinite plane that we need to put the dot, but some kind of, it's a triangle. Maybe it's a whole shape made of many triangles, like it's a mesh. Could be a graphical mesh, and we need to figure out which triangle the laser hits and where on that triangle to put the little dot. How do we do that? We need a point. We need a given point in our plane, and we need the normal of the plane. How can we get the point on a triangle? Well, we've got 3 points. A triangle has 3 points. Pick one. I'm going to pick A. Okay? So point A is our given point of the triangle. How about the normal? We just need the normal now. How do you get the surface normal of a triangle? And we raise our hands, and yes, cross product, exactly. Yes, cross product. So, and over there you're like, I can see you're puzzled. Let's look at how to get that from a cross product real quick. Let's do a cross product. Let's say we have some triangle, I don't know, A, B, C. We can take vector, let's say AB cross with vector AC, right? And if we, I'm going to do this with my left hand. You know, you choose right hand, choose left hand, whatever. AB cross AC is like so. Or AB, we'll do right-handed, AB cross AC is perpendicular to both AB and AC. That gives us a normal of the triangle. We would then, to get a unit normal, we would then normalize that answer, because the cross product is not guaranteed to give you a unit normal by itself. So now that we have this normal, we can calculate our D value, and we have our plane equation. Awesome. So we're right back now to what we did on the previous slide. We'll just solve the ray plane equation that we had. We already did it. We'll do the exact same thing. Now that we've got a point, it's the point on the plane, not necessarily the point on the triangle. So we'll need to ask, is this point inside the triangle, or is the point outside the triangle? So that's part 2 here of this solution. Part 2 is the point that we found, we take the point we just got from our intersection, and we say, is it inside the triangle like so? Or is it perhaps outside the triangle like that? And that question, I can think of at least 5 different algorithms, 5 different techniques to answer the question, is the point inside the triangle or is it outside the triangle? So you may be thinking of your way, lots of ways to do this. If you have no idea how to do it, let me suggest my way. I'm going to suggest a way involving the winding order of the triangle. Now, I do this one in particular because in our graphics labs, many of us have already encountered this winding order situation. Remember in the cube lab, the winding order, the order that you specify the indices determines whether the face points towards the camera or points away from the camera. If you just reverse the order of the indices, it reverses the way the triangle is facing. I'm going to use that same thinking to determine if the point is inside or outside the triangle. And it goes something like this. I'm going to break the triangle into 3 mini triangles. So I have triangle ABC here, or I could have ABP0. I have ABP0 is a triangle, and I have BCP0 is a triangle, and CAP0 is a triangle. So I have split my larger triangle into 3 small triangles. And what I observe about these triangles is their winding order all have to be the same. I have drawn my diagram here, ABC. So this is a counterclockwise winding order. So ABC, counterclockwise winding order. And so for all these triangles to be facing me, if counterclockwise is what faces me, all the mini triangles must also face me. And so I'm going to say ABP0, BCP0, and CAP0 all must wind counterclockwise, just like the big triangle does. But how do we determine that? Well, the way to determine that is with cross products. Another way of looking at this is, or a very similar way of looking at this, same solution, is to say, remember how I calculated the normal of my triangle? I took AB cross AC, perhaps, right? Let's take AB cross AC. Now, AB cross AC gives me a normal like so. And I want the normals of all the mini triangles to also face this way. So I will simply calculate those 3 mini normals. I already have the normal of the big triangle. Let's calculate the normals of the little triangles. How will I do that? This first one, I will take AB cross AP0. I will cross those. And then I will take BC crossed BP0. And I will cross those. And then I will take CA crossed CP0, and I will cross those. So each one using the same right-hand rule, boom, 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 boom. In the case of P0, I'm going to find all those mini triangles face in the same direction. But what happens with P1? Let's take a look. AB crossed with AP1. AB crossed with AP1 is not facing the same direction. It's facing the opposite direction to the way everything else faces. And therefore, I now know that point P1 is outside the triangle. So let's take a look. Let's take a look at the math for this. You take the 3 mini triangles and you cross them. Don't even need to normalize. I can save myself some effort. I don't even need to normalize. If they're parallel, if the answers of all those crosses are all parallel, if I dot them together, the answer will be positive. If they're anti-parallel, the answer will be negative. So that's all I care about. I don't have to unit length them. So I have the n that I calculated earlier. This is the normal of the triangle itself. And I will calculate the cross products of these little mini triangles. And then I can do a dot product to see whether they're parallel or anti-parallel. Okay, so that's how you do. It does involve a bunch of cross products. You did a cross product to get the normal of the triangle, and then you got to do 3 more cross products for the little mini triangles. Although, let me give you a note, and that is the only way the point is inside the triangle is if all 3 of those cross product dot products are all positive. And so, if you go back here and you take a look, you can eyeball method it to see that this first one is already going to be negative. So do that one first, right? If you're going to do it by hand, then look at your answer and say, or look at your triangle and say, This point is outside which line? I'm doing that one first. So because of this diagram, I'm going to do AB, AP1 first. That will come out negative, and I'm done. My answer is done. I don't need to do the other two cross products, so I can save myself a whole lot of work. And incidentally, if you're programming it, you can't know in advance, if you're programming it, which one it's going to be out of. But you can put an if statement there. You can do the first cross product, do the dot product, and then put your if. And then if it's negative, then don't bother doing the rest. Don't do the other calculations. A lot of times I see people that will do the three cross product, cross product, cross product, cross product, dot product, dot product, dot product, if statement. You can make it more efficient if you do cross product, dot product, if statement. Because if it's negative, you're done. If it's not negative, then you do the next cross product, dot product, if statement. And only if that is also positive, then you do the third cross product, dot product, if statement. Okay, so you can early out. Oh, and also let me repeat, there's lots of other ways to solve this. Let's do just a quick talk of what some of the other ways are. One way is to do the ray cast test. If I cast a ray in any direction from inside the triangle, it can only cross one of the edges. So what I might do is cast a ray straight down, let's say straight down the x-axis. This is something, by the way, that really only works in 2D. Really only works in 2D. So if I have a 2D problem, I can just cast a ray from that point straight down the x-axis. And so what I'm saying is, does this, I'll make a line, does this ray cross, find this point of intersection, is it in front of or behind point P0? And do the same thing for here, and then see, oh, this one's parallel, so there's no answer there. So there's only one line that ray can cross, therefore the point was inside. If the point was outside over here and I cast this ray, I'm going to get 2 times that it crosses, and that means it was outside. And if I do it over here and I cast the ray, I'm going to say there's 0 times that it crosses. So you can do that. That's a technique I've definitely seen before. Another one is to add up the angles. If I make these three mini triangles again, and I add up these angles here, these angles have to add up to the angles of the the combined triangle. And if you add them all the way around, you know it has to be 180 degrees. But in this case, it's not going to work out. So you can do a bunch of dot products. If you really love dot products, and let's face it, we love dot products, you can do a whole bunch of dot products to find the angles of all of the things and add up the angles and see if they add up to 180. If it doesn't work out, that's because you're outside. What else have I got? Area. We'll take these 3 mini triangles here and calculate the area of this triangle, the area of this triangle, and the area of this triangle. Add those together. It should add to the area of the big triangle. If it does not, it means your point is outside. How do you get the area of a triangle, you ask? You might remember that the cross product, like, I don't know, let's say AB cross AP0, let's say. The magnitude of this cross product equals the 1/2, no, that's the, I'm going to put the 1/2 on here. 1/2 the area of that cross product is the area of the triangle ABP0. That's That happens to be the area of a triangle right there. And so if you do that, you could do cross product, cross product, cross product, add them together. Comes out to a very similar equation to what we had with the winding order approach. The last one that I'll throw at you is barycentric coordinates. If you've learned about barycentric coordinates, you can convert this point into barycentric coordinates of our triangle ABC, and that will tell you right away whether it's inside or outside. How do you convert it to barycentric coordinates? A whole bunch of cross products. So you'll see that that math comes out extremely the same. So that's a whole bunch of ways to approach that problem. All right, it's been 30 minutes. Let's call that the end of this part. That's a whole bunch of problems you need to know how to solve when you're going into those technical interviews. And like I said, back in my Universal Studios interview, I got the ray reflection problem. Definitely be ready for that. I've seen other people giving the closest point on line, closest point on ray. For Insomniac games, I got this one, which is ray versus triangle in 3D. Yeah, these are legitimate questions you really do need to know how to solve, or at least have the confidence with the tools of your 3D geometry to be able to come up with a solution. You don't have to know it, like don't have it memorized. Don't make the mistake I made of going in thinking you had it memorized and just write it down. Go in and be able to use those tools and work those problems. Okay, so that's that section. One more video for this week, and we'll come back and do quaternions for the last part. See you in that one.